right, the last group of slides. Here we go. Let's get into this. So, we're going to start off in Chapter 7 here, talking about Lewis dot structures, or Lewis dot symbols, or just Lewis structures, whichever one you want to call them. What these are, this is a way for us to represent both individual atoms, although that's not usually the way this is used. Most of the time it is used to represent molecules, as we'll see in just a second. But before we can start drawing molecules, we have to learn about the individual atoms first, and then build from there. So the Lewis dot symbols show only the valence electrons of an atom or ion. And this is perfectly fine for us, because as you hopefully remember from the previous chapter, only the valence shell matters when it comes to bonding. If we're thinking about, and really just chemistry in general, for actual chemical interactions, the valence shell is where it's at. That is what is interacting with other stuff. That is where the chemistry is happening. The core electrons are important, they need to be there, but they're not actually doing anything. The valence shell is what's actually doing the chemistry, and so it's perfectly fine for us to only be considering the valence electrons in our Lewis structures. So when we're writing the Lewis structure for a single element, what we're doing is we're going to take the symbol for that element, we're going to pretend it is a box with 4 sides, and then we're going to distribute the valence electrons around each side of the box evenly. And we're only going to pair them up if necessary. Now here in this little example, they make a point of putting one dot here and then the second dot on the opposite side. It doesn't actually have to be that way. If you did BE dot dot, I would count that as being correct as well. But it does kind of look better if it's on the opposite side instead of being right next to it. But regardless, you fill in the 4 sides first, and then you pair them up if you need to when you're considering your valence electrons here. So what our goal is going to be, when we are writing structures using the Lewis dot symbols, is we are trying to get everything to have what we call an octet. When atoms make bonds, when atoms form bonds and share electrons or take electrons, as we'll see in just a second, they are going to be trying to get a full valence shell, which is going to be usually 8 electrons. The one really big exception to that is hydrogen. Hydrogen only wants 2, but almost everything else is going to want 8 electrons. And again, the reason it wants this is because if we go back and look at the number of valence electrons that the noble gases have, they have 8 valence electrons. They have a full valence shell, which is going to mean they have 2 electrons in their s valence shell and 6 electrons in their p valence shell. So for neon, that would be in the 2s and the 2p. Its 2s and 2p are full. The 2 shell is its valence shell, and so it has a full valence shell. It has a full octet. So everything is going to be trying to get that octet, with the exception of hydrogen. And by the way, the reason hydrogen is perfectly fine, having only 2, that's what helium has. Helium, a noble gas, has only the 2 electrons, and that is actually also a full valence shell, because if you only have 2 electrons, those are going to go into the 1s. There's only 1 orbital, 1 subshell even, in the first principal shell, and so that is in fact a full valence shell. So hydrogen is happy to be the same as helium. Most everything else wants to be like a different noble gas and wants to have 8 valence electrons. It wants to have that octet. So, in order to get that octet, things will either ionically bond, covalently bond, or perhaps metallic bonding, which we're actually not going to consider. We're not going to look at metallic bonding. But it is a thing that happens all the time. We're just going to mostly concern ourselves with covalent bonding. But just to remind you, if something is ionically bonded, that means that it is transferring its electrons from one thing to another, or it's taking electrons from something else, just depending on which one you're looking at. This is always going to be between a metal and a non-metal as well. So if you have a metal and a non-metal in the same molecule together, that is an ionic compound. They are ionically bonded. Covalent bonding, on the other hand, is where you have sharing of electrons. This is between at least two nonmetals. So if you have something like methane, carbon is a nonmetal, hydrogen is also a nonmetal, even though it's way on the other side of the table with the metals. And so this would be a covalent compound. It will have sharing of electrons, not complete transfer of electrons. All right. And so this is just going into a little bit more detail here about the Octet Rule. So it's talking about why potassium becomes potassium plus. And we've kind of already discussed this as well. So when potassium loses that one electron, it now has the same configuration as a noble gas, which means that it has a full octet, has a full valence shell that it discovers. We would call this a discovered octet. There are a few other exceptions to the octet rule that I'm going to cover here just very briefly. So helium, lithium, beryllium, and boron are all exceptions to wanting an octet. They would rather be like helium. The main reason just being that they're very small. They're closer to helium than anything else. And so it's actually easier for them to go down to be the same as helium than it is for them to go up to be the same as neon. And then there are some other examples of things that are exceptions that we're going to see later that actually have more than 8. We call these expanded octets. This is only possible if they have access to d orbitals, though. If they have access to an empty d orbital, then they're able to do this. But the really important thing here is that if we ever come across something that is going to break the octet rule that is not hydrogen, I won't tell you about hydrogen, but if there's anything else that breaks the octet rule, I will warn you beforehand. I will tell you, for example, if we have something like sulfur and it's double bonded to 2 oxygens and single bonded to 2 other oxygens, this is breaking the octet rule. As we'll see in just a second, each of these lines represents 2 electrons, and so this has significantly more than just 8. It has 12 electrons around that sulfur, which it can do, actually. If it was going to do this, I would warn you beforehand. I would tell you sulfur is going to break the octet rule. All right. So when it comes to ionic bonding and Lewis dot structures, it's pretty straightforward what happens here. So you would write the Lewis dot structure for potassium. It has 1 valence electron. It's reacting with chlorine, which has 7 valence electrons. And when it reacts together, the potassium is going to lose the 1 electron to the chlorine. And so this is written as K plus, and then square bracket chlorine with a full octet, and then a minus. So that is what the Lewis dot symbol for that ionic compound would look like. So you take the cation is always going to have a discovered octet. So this does in fact have an octet, but we don't draw it in. It's just understood to be there. But then you do draw in the octet on the anion, and you put square brackets around the thing with dots. So go ahead and pause the video here and give these last 2 a shot, and I will work it out when you come back. All right, so magnesium has 2 valence electrons. Oxygen has 6. 2, 3, 4, 5, 6. The magnesium is going to give up both of its electrons to the oxygen. And so what we're going to end up with is magnesium 2 plus that has a discovered octet, and then oxygen 2 minus with its full octet. This last one here is a little bit different because now we have 2 sodiums and 1 sulfur, but that's perfectly fine. So we're going to have Na with a single valence electron and then another one. Sulfur is going to have 6. And so both of these are going to be given to the sulfur. So we're going to end up with Na plus sulfur with a full octet, and then Na plus. All right. I hope that makes a certain amount of sense. Truthfully, though, Lewis structures are not usually used to represent ionic compounds. They're not nearly as useful in writing ionic compounds, but you should still be able to do this. I think there's 1 or 2 questions in the homework where you have to write the Lewis dot structure for an ionic compound. Where it is much, much more useful is writing covalent compounds. So this is when we have electrons being shared between 2 atoms. When you're sharing electrons to form bonds, that's what you do in covalent compounds, the bonds are always going to be made by pairs of electrons. So a single bond is made up of 2 electrons. And so here in this particular molecule, as an example, you have carbon bonded to 4 different hydrogens. And because of this, the carbon is sharing 2 electrons with each of those hydrogens. Now, normally it's not written like this. It's not written as 2 dots, just mainly because it's kind of hard to see what's going on sometimes if there's just dots everywhere. And so usually those 2 dots are represented as a single line. So each of these lines here represents 2 electrons forming a single bond. So when we look at this molecule, everything in this molecule is happy. The carbon wants an octet, and if we look, 2, 4, 6, 8 electrons. It has 8 electrons around it. The hydrogens do not want an octet. They only want a duet. They just want the 2. And each of them has their 2 electrons. So they started out not having all the electrons they wanted. Hydrogen only has 1 valence electron, carbon only has 4, but by sharing their electrons, they were able to get to a point where everyone was happy with what they had. And that is always going to be our goal in writing these Lewis structures, is to try to get everything, if it wants an octet, to get it to have an octet, and if it doesn't want an octet, then to get it its duet, if it's the hydrogen. So just another example here, oxygen and hydrogen. Everybody knows the formula for water is H2O, 2 hydrogens, 1 oxygen. And if we actually look at how those connect together in terms of their Lewis structure, the oxygen has 6 valence electrons. Each hydrogen has 1. So the oxygen is looking for 2 more electrons, and each of the hydrogens is looking for 1 more electron. And so they get together and they say, hey, I need a pair for this one. You need a pair for that one. Why don't we get together and make this happen? And then there'll be another hydrogen as well over here that would do the same thing with this one. And you would end up with this nice little structure, where you have oxygen with its octet, and each of the hydrogens with their duets. Now you might notice that while everything here is in terms of pairs of electrons, not all the pairs are the same. So these 2 pairs here are participating in a bond, And so we call these bonding pairs because we are super original in how we name things. And then these are what we call lone pairs. So it's still a pair of electrons, but they are not participating in any kind of a bond or anything. They are all alone. They're on that atom. And so they are a lone pair. They're not connected to anything else. And so we're going to see quite a few lone pairs and bonding pairs as we go throughout the rest of this chapter. There's a really interesting thing that can happen though. What if we had two oxygens? Instead of an oxygen and a hydrogen, what if we have oxygen that has 6 valence electrons, and it bumps into another oxygen that has 6 valence electrons? This oxygen says, hey, I need 2 more electrons to get my octet. This oxygen says, hey, I need 2 more electrons. Why don't we share? Why don't we take our 2 unpaired electrons, pair those up, and form 2 bonds between each other? This is what we call a double bond. More technical term is double covalent bond, but double bond for short is what most people say. And so once again, everything involved here ends up happy. The oxygen has its octet, this oxygen has its octet. Now we're just sharing 4 electrons in 2 bonds instead of only sharing 1. And that is perfectly fine. That is perfectly acceptable. We can take that a step further. Nitrogen has this Lewis structure. It has 3 unpaired electrons. It wants 3 more. So if you take a different nitrogen that has its own 3 unpaired electrons, we can form a triple bond. And so we have 3 bonds. I know this is kind of drawn strangely here, but that is 3 bonds between the 2 nitrogens. And so now once again, both of them have an octet. They don't mind sharing those 6 electrons in the middle as long as they end up with 8 total. And this is not limited to just 2 of the same elements, by the way. You can have things like this as well. This is called hydrocyanic acid, by the way. The acid form of cyanide, essentially. So super fun. So it's not just 2 of the same element that can form these double and triple bonds. It can be between any two elements where it's possible, where it would be preferable. It can do that. Alright, I think we'll call it there for this video. In the next one, we will talk about the basic rules for how to draw a Lewis structure, and then jump into some examples here of how to draw different things. So I will see you in the next video.